lot is because, of course, programming, it teaches critical thinking skills, it teaches problem solving skills, because once you've gone past that first initial language barrier and kind of got an handle of how to use a program, you have to figure out how to even write it. And a lot of that is problem solving and figuring out, how do I solve this task? And then applying your programming knowledge on top of it. We want our students to be creators of content, not just users. I'm sure all of us can pick up our phones and be like, there's apps on it we use. One of the cool things is students can actually get in there and program their own apps. They can write their own things for computers. They can write games, any sort of things. We want them to not just be a mindless consumer, but someone who actually makes these things as well. And of course, programming is something that comes up a lot in other STEM-related fields. So again, at high school level, which is what I teach, I have an engineering class. We teach programming in it as well. And a lot of students we get to it and they're like, oh, why do we have to do this? And I'm like, well, such and such, you want to go to Purdue for engineering. And did you know at Purdue in the first year engineering field, you're actually required to take a computer science programming class just to get past that first year. It's kind of a freshman requirement. So anything we can do to give students this sort of experience beforehand is beneficial to them in the long run. And as those of you who may have started to dip your toe into the water, if you give a man a program, you frustrate him for a day. And if you teach a man for a program, you frustrate him for a lifetime. It's a good sort of frustrate, but you'll find yourself continuing to just sort of tinker and work with things. So anyone out there is thinking, I don't know anything about programming, I don't even know where to start, I don't know, just like, I'm not qualified, that's okay. No one else does either. Most of the time, anyone who's working in computer science is probably Googling something daily. So for people like me who know a lot of programming languages, there's always like, okay, well, this works one way in this one language, and then if I go to the other one, it's something else, but I don't remember which language is which anymore. I'm just gonna Google it, and I'm gonna Google the most basic stuff daily. Even though, it's like, you should know what you're doing, and like, you even teach it. It's like, I know how to leverage what I know, and I know how to research the rest. And I know how things are structured, and that's kind of the goal of what we're teaching. It also helps to teach some really good research skills, to teach just the ability to basic Google things, because that's also something I noticed in my students, is a lot of time when we tell them to look something up, they're like, oh, it's not in that very first right underneath the search bar in Google. Google didn't pull it out of that first couple links. It's not on Google then. I'm like, no, you have to click the links. You have to actually look at it and, do some of your own research. But that's another skill we look at teaching. So where do you even start? You're looking at this program, you don't know why it works, you don't know why it doesn't work. You just don't even know what to do. There's some sort of crazy, absurd rules going on behind the scenes. You have to do these things, and if you don't, the whole program just disappears. Or the computer's yelling at you because there's no semicolons, and if you write the wrong thing, everything's broken. And then, of course, you create lots of bugs, and then you fix one and you make more. And there's so many other problems. It's like, where do you even begin? Well, the big thing we want people to do is just get in there and actually poke some buttons. Computer science, my analogy, if we think about throwing kids into the deep end, there really isn't a shallow end. So no matter where you start, you just kind of have to start. You want to, of course, get in there, maybe follow some tutorials. That's what we're looking at here today. But also kind of going in with the attitude that, you go in there and change things, see if it breaks, see if it doesn't. It's not like you're going to break the computer. We're working on a website. The worst thing it's going to do is say, hey, you can't run this code. You can't actually harm it. So it's just getting in there and just trying stuff. Big thing, if you heard us talking before we started, is copying and pasting is absolutely a good way to get started. You don't know what you're doing. Someone smarter than you already figured this out. I'm going to go copy their code, maybe edit it a little bit for what I need, until I don't feel the need to do that anymore. I don't need to go look it up, and I've kind of figured it out on my own. And of course, persistence is kind of like the big thing. Is, you have to actually check your code. You can't just say, oh, I wrote my program, I'm done, I'm going to turn it in. Because if it doesn't work, generally speaking, at my level, and definitely at the college level, what happens is they don't even grade it if your program doesn't run. And so that's another hurdle I have with my kids, is like, you have to test your programs. You can't just half-ass it and give it to me and say grade it. So you gotta try, and you gotta keep trying until something happens. And the big thing to get kids to understand is how a computer thinks. Is they're like, I programmed my program to do this. It's not doing this. Computers are very literal. It can only do what you told it to do, and exactly what you told it to do. And when that doesn't happen, they get frustrated, and so do we all. But that's kind of the big thing there. And from there, I'm going to actually stop at this, and we're going to jump over and actually start doing some programming. Oh, let's jump over to this one. There we go. So what I've got, I'm in again, this is kind of like this is kind of an example of a student view of what you would see in Autodesk Tinkercad in terms of account, where they haven't started doing anything yet. I'll show you a little bit back end of what the teacher sees later on. But the first thing I'm going to do is jump up to my search bar, little magnifying glass, search for circuits, and I'm going to search the word Broncos. It's our school mascot. It's a very unique term because there's an H in it. Nobody else does that, so I know if they're looking up stuff, they're only going to find the stuff that I created. You can have multiple tags. I only needed the one. I'm going to copy and tinker it because we're doing task 3 here. And we wait for it to load. So I've got my Arduino, I've got some circuits, I got a whole bunch of LEDs this time. I've got this really suspicious hole in the middle. If I open up the code, I see there's no code started for me. That's a bummer. I'll have to actually use my brain. And then what I'm going to do is jump over. I won't share it on this screen just so it can maximize the space for seeing the code and seeing the Arduino. But looking and following along the guided activity for task 3, what we want to do the first thing is just sort of finish the circuit. So I'm going to actually go ahead and close this code window. And what you would do, there's some videos that go over this. I'm going to go through it a little quickly just for the sake of so we can talk more about the program than circuit building. I need to add an LED. Click and it'll drag it out. I'm going to follow the color pattern. You don't have to. And I'm going to go ahead and slip this in here just like all the other ones. I'm going to grab a resistor. You can also copy paste components, but I don't know. I just didn't. I'm going to wire that up. Grab from here. You could go straight to the port. I could go to any other port if I wanted to. I technically could go anywhere 5 to 0. But today, with what we're going to do in the latter half of the activity, you really need to go for this port that's in sequence. Or else it just makes your life more difficult later. And nobody wants that. So very quickly and very easily, I've got a completed circuit. Just getting a little more familiar with the hands-on portion. Because in computer science, unfortunately, there's not a lot of hands-on, just a lot of typing. And, in this case, if you're working with a real Arduino, you could actually wire that up. But, let's see. We've got some work to do. We gotta do... The goal here is to make these LEDs do a chase sequence. So think of it as the top LED turns on, and then the second one, and it kind of, like the light would be blinking and circling through those 8 LEDs. The first thing we're going to look at is, of course, we need to set up our program so that way I can even use these. And if we've learned, hopefully from previous activities, how we want to do that, first thing I take stock of is what pins am I even using on the Arduino. I'm using 13 through 6, okay? And so we should be in setup. And remember the code, it's pin mode, with capital M. 13, and then the word output all in uppercase with a semicolon at the end. And this is where copy and pasting really is going to come in here. I need 8 of them because there are 8 LEDs. I'm going to go ahead and down this line. Just replace all the numbers. Everything's set up. Hooray. So what we need to do next is kind of think about and think through how I'm going to make a chase sequence. So what I'm going to do is I'm going to use this section here in the middle, just for right now. You don't have to, but this is kind of the example, because I want to do more than just talk about it verbally. So we're going to write a little bit of pseudocode, and what that is, it's not code per se. I can't copy and paste it into my program and make it work. That's why I put it in a comment. So that way we can see it and reference it, but I also, it won't hurt the program at all because I want to think about what does chase even mean. So I want that top LED to turn on, then the next one, and then the next one, and the next one. So what that means is I want, LED 1 turn on, and then I want to wait so I can actually see that LED being on. Then I want LED 1 turn off, because, if I want the light to appear like it's moving, it has to go from one LED to the next. And then I need LED 2 to turn on, and then I need to wait so I can actually see it being on. LED turn off, and then what would happen next? I would move on to LED 3 and turn it on, and then I would wait. LED 3 turn off, and then kind of so on and so forth. And that would keep going until at the end, of course, I would see LED 8 turn on, and then I would wait. LED 8 turn off. And then what would I want to happen next is after this LED turns on and it turns back off, well, I want this one to turn on. But I already have that. So really what I would want is for the program to kind of loop to top. And this is something that the Arduino does. Ooh, there we go. And kind of put an arrow. So, of course, that's how our structure of our loop works. When I reach to the bottom of the loop, it goes back to the top. So I would be back at what I wanted to do in the first place. So what this is, it kind of gives me a structure for figuring out and understanding what I should be doing kind of going forward. And I need to figure out what are all the things that I need. Well, the first thing I said I wanted was to turn the LED on. And from the earlier activities, and it is a prompt question, of course, in the guided activity, is what does that even mean? How do I do that in the Arduino language? Well, I use the digital write command, and in this case, LED 1 is going to be 13, it's the one at the top, and I turn it on by using high. And what I'm doing is I'm turning this pseudocode into real code, just sort of getting an idea of what it would look like. How do I wait? Remember again from previous activities, but also in this activity here. So that way, in case somebody forgot, it's written out, it's the word delay, followed by a number, which is measured in milliseconds. I want my chase sequence to be kind of fast. I'm going to go ahead and pick like 200. Pick a number. Obviously, this is going to be determines how fast your LEDs blink. So you don't want to pick it too slow unless you really like a slow chase sequence. And of course, the last thing I need to figure out is how do I turn it off. Remember from last time, that's also our digital write command. And you would keep doing the same sort of thing. You don't need to actually go through and put every line of pseudocode equals this, because that's what you're about to actually do to write the program. I did this so we can kind of see how they go between the two. Okay, very cool. So I'm gonna jump on down here, paste some of that in. And what you don't have to put a space between the commands for the LEDs. I'm doing it just for the sake of some clarity. What I'm going to do is also copy and paste all of this. I'm going to change it to LED to 12 for the next LED. And that way it kind of just breaks it up. I'm going to go ahead and test my program and see if it even starts to work the way I think it should. So, okay, we're blinking between the first two. They're definitely turning off. It's a little hard to see. I think it's because I only have 2 LEDs, so it's hard to tell. I'm going to go ahead and copy both of these now. Just so that way I can generate some more. I can be efficient while copy and pasting. So I'm going to go ahead and throw those in there. Let's see how well we're doing. Very cool. We're getting a chase sequence going on. Tinkercad at the beginning. I don't know how well it went across the screen share. For me on my end, it was a little laggy, so that's something maybe later on I might play with my delay time, just because I want my program to simulate as smoothly as possible, and sometimes your internet speed will depend upon that. Now, I'm going to copy and paste all of this again, because why type it when I can just change only the one thing that I need each time? So I get all the way down to the bottom. I've gone through all of my LEDs. And if I run them, I've now got an actual cheese sequence going on, which is fantastic. It's slowly getting faster to where it should be for the delay time. Tinkercad is running a little slow for me this morning, it seems to be, but it's running pretty smoothly, and that's cool. What you would do is just you would continue. This is kind of the end goal for this section activity, because this is not really the goal for this whole guided activity. This is not the goal of task 3. The goal of task 3 is to learn something a little more complicated. So what we've done so far is leveraged our ability to turn an LED on and off. It's what we've kind of been learning the last, 3 activities. I know how to turn an LED on and off. I know how to do that really well now. But I want to get a little smarter now, because the thing to take note of, and the thing to try and get kids to pay attention to, is that this is really, really repetitive. What this is it's like I'm doing the same thing over and over again. There's gotta be a faster way. Obviously, spoiler alert, there is. So what I'm going to do is I have commented out all of that code. You'll notice I was very careful to put the end of that comment before this curly bracket, because if I had to put it afterwards, the program would yell at me. What it would do is if I'm like, oh, I just went all the way to the bottom and I tried to run it, it's going to throw an error, because it's going to say, you have, this is an unmatched pair, and it's very easy to accidentally do that. And I don't want to do that. I want to start in and do something really cool. And this is one of those ones where it is very much the line of, my philosophy here is I do something, then we do something, then you do something. This is very much kind of an I and we, where I'm just going to be like, here's what you're doing. You don't necessarily need to understand it yet. We're just going to do it, and you're going to see what happens. Because if you follow the guided activity, the next thing we're going to actually introduce a concept called the for loop. And what it is to repeat statements. Yes.
Okay, we got a couple questions before you move on.
Okay.
All right. So the one question says, if we have nothing for CS, what do you recommend we purchase for a class set of 36 students? What budget would you recommend? And they have a couple of grant sources they can probably ask for the money.
Well, if you're looking to get physical Arduinos, there are a couple places, and I can drop some links a little bit later where you can get kits.
I'll drop the link that we sent out to everybody. How about that?
I think that's the one we bought for our classroom. They're probably the most cost-efficient kit that we've found. It doesn't come with a ton of peripherals, but it comes with some basics, and then a lot of stuff like LEDs and resistors you can buy en masse for like dirt cheap.
And they're about $37 roughly.
Yeah, and it comes with a little booklet, though I included that in the resources. We'll talk later. It's got an Arduino, a breadboard, the wire you need, some very basic like LEDs, resistors, potentiometers. I think the Arduino itself is around $20-25 or a little more nowadays. I don't remember. I haven't bought one by itself in a while. That would be a good place if you're looking to use Arduinos. The nice thing about computer science, though, is if you're on a real tight oh my gosh, words. String budget.
String budget.
Yeah, I can't say the word shoe this morning. Is most of it is entirely computer based. Tinkercad is totally free, and unless they change that, I don't expect it to. At the moment, everything I do with it, including classroom stuff, is completely free. So everything we're doing is something you can do for no budget at all. So if you have a classroom set of computers or kids are 1-to-1, that's like the most cost-efficient option, because there is no cost besides having devices. Beyond that, things like Arduinos, it's helpful to have, and we'll talk about them with the task 4, things like potentiometers, keeping it with the more simple components. Some of the stuff later on, it depends. You very quickly starts accelerating the level of computer science to use and programming knowledge to use more complicated peripherals. But you can do a heck of a lot with just LEDs. And maybe up to a 7-segment display, which I want to say that kit might have come with. I don't remember.
Well, I'll send the link here in a second.
Yeah.
So the other question was, and I think you answered this, but does each student need an account? Is there an annual fee for, and they said, Arduino, but
Yeah,
I
so
think
either way, so through Tinkercad again is free. Um, each kid needs their own account, sort of, and this is something I'll address a little bit later, is when you create a classroom, they kind of get an account in that classroom, per se. Um, I promise I will get to that question. It'll be a little easier when I can show all of that as well. But again, as far as I know, that's all free. And Arduino's, if you use the physical software, is totally free. It's open source, even, and you can just download it. Doesn't even require an admin install, so you don't even need to mess with your IT department. Though you probably should talk to them just so that way they stay happy. Um, but I will address a lot of that a little bit later at the resources, and we go through and kind of show you how to go in and actually do all that fun stuff from the back end.
if everybody could please use the chat option and not the question and answer. I know that sounds really weird when I say that out loud because we're asking questions, but the chat option, and if you would send it to all panelists, that way both Jill and I see the question, that would help us a lot. So just use the chat option, please. Thank you.
Okay. So what we want to do, and going back to programming a little bit, we want to make this program really efficient. And what we're going to do is use something called the for loop. If you're looking in the Word document, the guided activity, you got this big loop. It's like, oh, here's all these parts. From what I've seen, most people look at that and they're like, okay, I don't know what's going on there at all. That's a whole bunch of words, and it's like the type of loop, there's this loop control variable, there's conditions, there's increments, there's the body, and there's a whole bunch of weird vocab. Cool, let's just dive in and ignore all of that and just type it the way we see it and figure out how it works. So what we're going to do is just sort of kind of demonstrate how this works. And what I'm going to do is going to use the serial monitor, which we used in task 2, just to kind of show you how a loop works. Begin. I can spell. And what I'm going to do underneath, I am going to type exactly what it says in the activity. So I'm going to use the word for, because it is a for loop. You'll notice it turns purple. It is a keyword. Int for integer type I, and then set it equal to 1, semicolon. I is less than or equal to, so just the less than and then the equal to, 13. And then I'm going to use I++. And then I am not going to write a semicolon. I am not finishing this line. I'm going to do similar to what we see going on with the void loop and void setup sections, is I'm going to use an open curly bracket, go to the next line, and what I'm going to do right now is I'm going to go ahead and close it, so that way I can't forget to close it. And then I'm going to go in and add the stuff in the body of my loop, the inside part. And all I'm going to do is going to do a serial.println. So again, that's print ln. It's an L, not an I, not a 1. And I'm going to put my variable I on the inside. And what I'm going to do is I'm going to open my serial monitor. It's not important to the chase sequence to use a serial monitor, but we're going to show you how a loop works. And I'm going to run it, and then we'll talk about why it does what it does. So you'll notice what's going on is I've got the numbers 1 through 13 continuously being counted and added over and over and over and over again in the serial monitor. 1 to 13, 1 to 13, 1 to 13, over and over and over. Cool. Neat. Okay. Let's poke some other buttons. I'm going to go and clear this so I know the difference between, what's going on. I'm going to change this value of I. I'm going to make it a 5. Okay, 5, 6, 7, 8, 9, 13, 5 through 13, 5 through 13, over and over again. Neat. Okay. I'll clear that. Let's see. I'm going to make this -10. Okay, we started at -10. We're going up all the way to 13. So -10 goes to 0, goes to +13, back to -10. So it jumps from 13 to -10. Okay, but otherwise it's going up by steps increments of 1. Very cool, interesting. And then this last one, I'm going to say, let's see, what about 13? Hmm. 13, 13, 13, 13, 13, 13. I got one more I should check. Accidentally skipped it. 15. Nothing. Program's running. Nothing. So, what we're gonna do is sort of talk about why all of that did or did not happen. So, when this was 1, I equals 1, what it does and how a loop works is it goes in and says, whenever a condition is true, and that condition is in here, it's the inequality I less than or equal to 13, it's going to do what's inside of here. So, it's going to say, okay, serial.println I, and the value of I at the beginning was 1, so it's like, 1! And then what happens next, you can kind of think about it happening on this line with the curly bracket. It's something that happens in the loop, just a feature of the loop. It goes and uses our increment, which increases the value of I by 1. So here it goes, oh, I was 1, now you're 2. And now, kind of like we do with loops, think about this flipping to the top, to the start of the loop. It's going to say, hey, is the value of I still less than 13? Well, 2 is less than 13, so that's true. So it's going to be like, cool, I'm going to print 2 then, because I'm printing I and the value is now 2. It's going to flip to the bottom. It's going to be like, okay, you're 3 now. Goes back to the top. Is 3 less than 13? Yes, it is. It's going to keep doing that over and over again. It's going to do it until, we've printed 12. It's going to say, okay, 13, you're 13 now, I. Well, is 13 less than or equal to 13? Yes, it's equal to 13. So we're going to serial.println, it's going to be 13. We're going to output that 13. It's going to, the next line, it's going to increment I. It's going to go from 13 to 14. It's going to flip to the top. It's going to, well, is 14 less than or equal to 13? It's going to say, no, it's not. And say, well, I'm done. I'm going to skip what's over here, and the loop is over. And now, since we're inside a whole bigger loop in the Arduino, it goes back to the beginning, and I get set back to being 1. This first one only happens the first time. And then every other time it's checking conditions and setting this, incrementing it. So when I started all the way down at -10, it had to work through a lot of numbers to get up to 13. When we started at 13, it never left 13 because it couldn't go anywhere. And when we started at 15, what happened is it's like, well, it started at 15. 15 is not less than 13. It's actually greater than. So it never actually ran the loop. And that's why when we ran it at 15, nothing happened. Because 15 is never less than 13. So we just get to sit there and watch nothing occur. And what we're going to do now is I'm going to change this. So that way we can start using it to make our chase sequence. I'm going to go ahead and comment out this serial stuff, because I don't want that. I'm going to delete this one. And I guess I could leave it in, but I'm going to just do the LED stuff. I'm going to copy and paste my LED control. And you see the formatting got a little funky there when I copy and pasted it. This is where, if you went to one of the earlier sessions, you'll remember I talk about why following good convention and indentation is important. Because when you start doing things like for loops or other loops, or putting loops inside of loops, you'll notice there's some very intentional indentation going on. And if anything that's kind of here, I generally assume is being inside the loop. I want things over just one more, so I know it's inside the for loop. So I'm going to go ahead and back it up and hit enter. It gives me very clear, when I am looking at this at a glance, I know where something belongs, without having to go through and kind of figure it out. And what I'm going to do is cut a little bit to the chase, because I definitely want to spend some time talking about the next activity, is I'm going to replace the number with I, because I can replace anything with anything that's going to be a number with I. If I wanted to, I could do the delay. That would be silly, though, and that would be weird. I could make some interesting blink patterns. But what this is going to do is it's going to actually kind of change my chase sequence. And when I run it, now in this case it's chasing opposite of the way we did it before. That's because my numbers are increasing. And, before I was kind of calling the top, I was going top down. Obviously this time I'm going from 6 to 13. But I very quickly have the same essential chase signatures that I did before, but instead of having all of these lines of code, I've got this tiny section of code. And the fun thing there is now if I wanted to make it blink slower, I only have one delay to change. If I want it to go super fast, I don't know how well this is going to carry across a share screen. It goes a lot faster. And that's fun. So, things you could experiment with and have kids play around with is like, what does it look like when I change these numbers? Obviously, if I change the ending from 13 to 10, it only goes up to the LED that's plugged into port 10. And if you're wondering about how I would get it to go back down, the same way we had the loop at the very beginning, well, I can flip all of my conditions around. And I can have it go the other way. And instead of incrementing the value of I can decrement and just use 2 minus signs instead. Slow this back down a little bit. And it'll work the other way. Now it's kind of similar to how we started. You can have them go both ways. It's all about how it runs through the loop and does the math. In this case, it's going from 13 to 12 to 11, etc. because it's decreasing. And it helps so much quickly. I can work a lot faster with these loops because I'm using a repetitious task and I'm using repetition statements for it. And you can play around a lot more with what you can do with that. Unless there's some really burning questions, I am going to move on to task 4 so we can talk a little bit about working with some new components, not just LEDs. So of course what I'm going to do, come up, get a new template. So now I've got this new circuit, new things. I've got this weird blue thing in here. It looks like a dial, kind of is. So if we were looking over here, you'll notice it's called a potentiometer. Very quickly, nobody says potentiometer anymore. Everyone says it's the pot. And then kids giggle, which is funny, and that keeps them happy. So, whatever. There's some new stuff. There's got some more wires. We're using our 5-volt power wire. I've used ground, and now I've got this other wire now going into this new section of the board I haven't used before, the analog in section. So that's something different. And what I also would encourage you to sort of get an idea of what else is going on. And a potentiometer has got 3 legs. It's got these 2 terminals. It's for power and ground. Totally interchangeable. Doesn't matter which one's which. In the middle is the wiper. That is your signal. And that is the one going into an analog port. And that port in this case is A1. And then of course I've also got some LEDs set up. Very nice. Let's look around and see what's going on in our code. Okay. So I've got all the pins look like they're set up for my LEDs. Okay, I don't need to do that. Looks like we're going to use the serial monitor, so I'll go ahead and open it up. And I've got some code here. It says integer, so that's, again, we're creating a variable of the integer type. We named it pot value, because I don't know about you, but I don't want to type the word potentiometer out a lot. It's a long word. And we're using this analog read command. That's new. And we'll see this is actually incomplete for right now. And what we have to do is inside the parentheses, we have to actually put the port that the potentiometer is plugged into, which again, we established we looked at our circuit. That is port A1, and that is its full name. It is not like 1, it's not A, it is A1. There is a letter and a number. And okay, very cool. And I'm just gonna kind of follow along exactly what we need to do. And I'm going to tell the serial monitor to print whatever the current pot value is. So wherever my potentiometer has been spun to, it's going to tell me that value. So I'm going to go ahead and run it. Now, this is one of those things where I think I am fighting the speed of my computer a little bit. Oh, well, goodness gracious. That should be the word begin. In setup, that's at serial.print instead of serial.begin. That would be why things aren't running. There we go. So right now, it's just giving me this number 246 over and over and over again. And my potentiometer is just here. So once the program is running, I can actually click on it and kind of spin it. Now, here's your caveat. In the real world, when you spin it, and if you have a real Arduino connected to a real computer with a real potentiometer, those numbers will update nearly instantaneously. On Tinkercad, there is a considerable delay because you are fighting the speed of the simulation and the speed of the internet connection you have, and there's only so much we can do about that besides being really patient. But as I spin it around, I can get different numbers. Yeah, I'm going to go ahead and spin it all the way to the top. Let's see. My maximum value is 1023. And my lowest value, if you saw from earlier, I'll spin it all the way back down to the bottom. Wait for it, is 0. So I have a range on this potentiometer, 0 to 1023. Now, where you might have seen one of these types of things before, potentiometers, think about volume knobs, maybe like certain dimmer lights, things like that. That is the same sort of technologies going on. As you're spinning, it's sending a signal relevant to where its position is. What we want to do, though, is learn a little bit about something called the map command. And the reason we're doing this is, say, maybe sometimes I don't want to go from 0 to 1023. Maybe I want a different range. So I'm going to go ahead and stick it kind of in between here. I'm going to make a new variable. This is going to be my mapped value. I'm going to use the map command. And how it's structured is your first thing is the value you want to change. So this is the value coming in off the potentiometer. So I'm going to change pot value. The old minimum and the old maximum. So that's 0, 1023. And then whatever I want it to change. So we're going to start from 0 to 255 and we'll put in some different numbers. And instead of printing pot value, I'm going to print the mapped value. Okay, so I still got a string of zeros. 0 does map to 0 because that makes some sense in this case. Because it is my minimum value in both cases. And as I spin it all the way up, the maximum my dial can go to is 255. And anything in between is now kind of set between there. And I'm going to cut to the chase a little bit. And the reason we like to use map as opposed to, some of the kids ask me, why can't I just divide it by a number? Well, I don't have to go from 0 to 255. I could use custom ranges like -100 to 100. I can get a lot of different value out of this. Before, if I were just dividing by a number, I can't get to those negative ranges. Now I have total control over that sort of thing, and it depends on what I want to do. What I'm going to do is actually leverage this. So the goal of this objective, of this activity, is to spin this potentiometer to control these LEDs and kind of think of it as a sweeper. So when the potentiometer is all the way to the left left LED is on. When the potentiometer is all the way to the right one's on, and these two somewhere in the middle. So I'm going to map my potentiometer all the way down from 0 to 3. That's going to give me 4 output values, which works out really well because I have 4 LEDs. So you see I can get to 2, I can get to 3. There's 3. I spin it over here. Should be in the 1 range, maybe. 1 and 0 are in there somewhere. We can get to all these values. I can use them. So the other objective of this activity is to learn about things called conditionals. And what a conditional statement is something you definitely have used before. You just may not know it by name. And this sort of the example is thinking about what you might do if it's raining outside. So something I might do is carry an umbrella. I might wear some rain boots. I might stay inside. If the weather is equal to rain, I'm going to do these things. If it's not, I'll do something else. And so that is a type of conditional. And what we're going to actually do here is use a different one. This one's going to actually be called a switch case. And it's called that because that's It's verbiage. It's what the whole thing is structured around. It's got the word switch, it's got the word case. So the controller that I'm kind of using here, this variable we're switching on, is the mapped value. So let's look at how we can use this in our program. Again, I've got this open curly bracket, so the first thing I'm going to do is go ahead and close it immediately so I can't forget later on and then have the program yell at me. So what I'm going to do inside, now I'm going to actually do something that's going to be called case 0, and now this is a little different. We are using a colon, not a semicolon. And I'm going to go ahead and tab this over. This is one of those things that's a little more sensitive. And do you need a potentiometer for each kit? I would say if you're trying to do this with a real Arduino, you would need one. I want to say the kit that was linked in the chat does come with one. Again, like a lot of electronics components, potentiometers and those things are really, like, super dirt cheap. I'm talking, like, you know, maybe, like, they might be 20 cents a piece, maybe a little more. A lot of these breadboarding type components are nice and affordable. So what I'm going to do is thinking back, I'm not going to write the pseudocode out for this. I'm going to think, what do I want it when it's 0? Well, I want the far left LED to turn on. So that is LED, it's plugged into port 12. How do I turn an LED on? Well, I'm a master of turning LEDs on at this point. I can do digital right high. I do put a semicolon here. And this is one of those things where it's just kind of a law, and we'll talk about why in a little bit. I'm going to use the word break, and then with a semicolon. And for right now, I'm going to go ahead and put everything else in here. I'm not going to fill them out yet. And good convention is I'm going to use a default here at the bottom. I'll fill those out later. So right now, let's see. My potentiometer last was set to 1. So that'll work out for me in this case. Oh, what did I do? I did something funny. 44. Open. 1, 2, 3, 4. Okay, what did I do? I bet it's something in here. Let's find out. Yep, something in there. I did something silly. I do not like these being empty. Huh, didn't like that being empty. Okay. I will put the break command in there. Good enough. That's fair. I understand why. Default has to have a break. It has to do something, or otherwise it would yell at me. Again, the exact why there doesn't truly matter. Now, you notice my LED's not on, if we remember from our serial monitor.